Another type of differential equation. This time we will discuss about the exact differential equation. So the idea is that if a given differential equation has variable separable, or we can separate the variables, so we'll just simply separate the variables. Or if the variables cannot be separated, we can check if the given differential equation is a homogeneous equation. So this time we will discuss another method or another type of equation where in this time it is an exact differential equation. So for the exact differential equation, this is another type of differential equation that can be solved directly without the use of any of the spatial techniques. So it should be a first order differential equation, and it is called an exact or exact differential. So the idea is that for a certain differential equation, so this is our general form, which is m of function xy dx plus n function of xy dy is equal to 0. So this is considered as exact if and only if that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So this is the first thing to do, is that to test if the given equation is an exact equation. And then we have the steps. So we have to test first if the equation is exact using the test for exactness. And then we have to integrate the coefficient m of dx. We have to integrate with respect to x, and then this time, because we will consider the partial differentiation or partial derivative, so we have to ignore the arbitrary constant. And then also we have to integrate the coefficient of dy, which is n, as function of xy with respect to y, and again we have to ignore the arbitrary constant of integration here. And then we have to merge the two expressions. We have to write down each term exactly once, and even if a particular term appears in both results. So that's the idea how to find the general solution for an exact differential equation. Let us have a solution here. Our first example is we have y squared minus 2x dx plus quantity 2xy plus 1 dy. So if we are going to analyze the given differential equation here, the variables cannot be separated. So we cannot apply the variable separable. Then we have to look for another method. Let us check if it is a homogeneous equation. Now in homogeneous equation, the power of the given variable should be the same. This is raised to square. This is only raised to 1. So they are not the same. This is a square, and then it is 0 degree for the 1. So understood, it's not a homogeneous equation. So the other way is that let us test or let us check if this equation is an exact equation. So say the coefficient of dx, which is m, is y squared minus 2x. And then we have to look for the derivative of this with respect to y. And the coefficient of dy, which consider as n, also find the derivative of it with respect to x. So for the m, finding the partial derivative of m with respect to y means understood that x is constant. So we can only find the derivative of y squared here. So this is 2y. And then the negative 2x is 0, as consider as constant. And then for the coefficient of dy as 2xy plus 1, we have to look for the derivative of n with respect to x, meaning to say that y is constant. So derivative of 2xy wherein y is constant, and we can only find the derivative of x as 1, so this is 2y. Then understood that the partial derivative of m with respect to y is also equal to partial derivative of n with respect to x, which is equal to 2y. So therefore, we can say that this is an exact. So if the differential equation is an exact equation, here is our solution. We have to evaluate or integrate the coefficient of m as dx. So this is now integral of m, function of xy, partial derivative of x or dx. So we have y squared minus 2x dx here, wherein y is constant. So we have y squared and then integral of dx is x. And the negative 2x dx is negative by power integral. So we have negative x squared. And also we have to integrate the coefficient of n dy. So this time we have to consider the x as our constant. So we have 2xy plus 1 and then dy. So we can evaluate the y here wherein x is constant. So we have y squared over 2. So we have to reduce the 2 there and then we have xy squared. And then the dy, integral of dy is y. And then all we have to do is merge. So we have our solution as the function f of xy is now obtained as xy squared minus x squared plus y. Now if you will notice here, the xy squared should be written once only. So as you can see there, we have both xy squared and xy squared from step 2 and step 3. So therefore, we only write once for that variable. So this is simply xy squared and then minus x squared plus y. And since the function xy is equal to c as our general solution, therefore we have xy squared minus x squared plus y equal to c to be our general solution for that differential equation. Another example is x times quantity 1 minus sine y dy, and this is equal to cosine x minus cosine y minus y dx. Now, as you can see here, it is not equate to 0. So it is not in a general form of differential equation, first order, first degree. So understood is we have to simplify this equating to 0. So then we can transpose the quantity cosine x minus cosine minus y dx on the left side. So it becomes now negative. And then we have to multiply by negative here. So this is now negative cosine x plus cosine y, and this is plus y dx. And plus x times quantity 1 minus sine y dy equal to 0. So in this equation, the variables cannot be separated, so we cannot apply the variable separable here. And then it's not homogeneous because they are of different power or exponents for the variables. And then let us check if this equation is an exact. So we have the coefficient m here for the coefficient of dx and coefficient of n as for the coefficient of dy. So this is our first step. We have to test for the exactness. So our m, which is coefficient of dx, is negative cosine x plus cosine y plus y. Then finding the derivative of this m with respect to y, wherein x is constant. So negative cosine x is constant. And then we can find the derivative of cosine y. Derivative of cosine is negative sine. So we have negative sine y here. And derivative of y is 1. Or we can rewrite as 1 minus sine y here. And then for the coefficient of n, which is for coefficient of dy, so we have x minus x sine y. This time we have to find the derivative of n, partial derivative of n with respect to x, where x is constant. So derivative of x is 1 and derivative of x is 1. So we have sine y as the constant. So we have 1 minus sine y. Now here, understood that the given equation is exact because the partial derivative of m with respect to y is also equal to partial derivative of n with respect to x, which is equal to 1 minus sine y. Then we can continue as for the solution of exact equation that we have to integrate the integral of m as function of xy and then partial dx here. So, understood that we will consider the y as constant. Excuse me. So we have here integral of negative cosine x dx. So the integral of cosine is sine. So we have negative sine x here. And then for the cosine y dx, so cosine y is constant, so we have x cosine y. And then y dx, so y is constant, so we have xy here. For the integral of n as coefficient of dy, can now be integrated by dy. So we have x times quantity 1 minus sine y dy. And this is now considered as x is constant. So x here is constant. Then we'll just evaluate the 1 minus sine y here. So when we distribute the dy there, so we have the integral of dy as an y. So we have xy here. And then we can evaluate the integral of sine y dy. Integral of sine is negative cosine. So negative times negative is positive here. So we have positive x cosine y. And then the next step is that we have to merge the two function, the left side and the right side, the m and n. And we have to follow that the function xy now is equal to negative sine x plus x cosine y plus xy. And again, this time, the xy and x cosine y should not be written twice. So we'll only write once. So we only have the x cosine y and xy once. Therefore, since our general solution is f of xy equal to c, therefore our solution for that differential equation is xy plus x cosine y minus sine x, and this is equal to c.